All right, this is ISAT 430, Materials and Manufacturing Processes, Lecture 6, Metal Casting. All right, so today we're gonna talk about mainly about casting or shaping of the metals, and for metal casting, it's a process in which the molten metal flows by gravity and all some other force, for example, a piston and push into a mold where it solidifies in this shape of the mold cavity, and so basically, first we melt metal and then pour it into the mold and then let it cool down, and solidify to a shape of the cavity. So the process is similar to plastic injection molding. But in casting, first we pour it. One process is we pour the metal, and another major process is we're gonna use force to push the liquid into the cavity. All right, so advantages and disadvantages about the casting technology. So the advantages include that it can actually create very complex part geometries. As long as we can make a shape, whatever complex it is. So because of the liquid, it can flow wherever we can. So that's why it can easily make some of really complex geometries. And also, the casting process is nice shape. Means that we do not need some other processes to modify its shape. But sometimes some subsequent processes, for example, grinding, or machining, may be used just to give a nicer surface finish, because the casting process does not give a really good surface finish. And also we can produce very large parts, as long as we can make a really large mold, and and we can make a really large parts out of one casting. So for example, in the future, actually already happening in some of the companies, that in the car frame, instead of putting a lot of metals together, welded them together, actually it can be casted into a one single body shape. So the benefit of that is, in the past it's probably going to be a lot. In the past, maybe there were a lot of processes in order to make one single car body. But if you use casting, actually it's only one process we can make it, and that's a lot of saving of the cost, and also energy, tools and equipment, making it more economic. Also, there are some of the disadvantages. For example, there are a little bit of limitations on mechanical properties. For castings, there are when you cast some of the metals, and at certain places, the strength is probably just not as high as either assembly or welding. So in this case, maybe there will be the little bit of limitations on that. And also, dimension is not as accurate as some other processes, and also surface finish is not as good as well, because of the shrinkage. Right, whatever material, there's a thermal expansion. So when you solidify or cools down, actually the dimension or the volume actually changes. So that's why controlling dimension can be a challenge for casting as well. Same with safety, because we're dealing with hot melted metals. So inevitably there will be some safety hazard risks for humans to work with them. All right, for casting process, one big part is the mold. We have to carefully design the cavity, cavity, so that we can create a good part geometry. And when we are designing the cavity or designing the mold, actually we are making the mold size a little bit bigger than is required. or than the actual dimensions is because just to compensate for the shrinkage of metal during the solidification and cooling. And usually, if we are really looking at high accuracy of the part, then usually we're gonna follow up with some machining processes to achieve the dimension we want. For the mold, it can be made of many different materials. For example, sand, plaster, ceramic, and metal. You can see all these materials have high melting temperature. Sand, mostly it's a silica, so we know that's it's a really good material for factory equipment or materials for a process to deal with high operating temperature processes. All right, now let's look at this this whole this mode. There are several places we want to see. Well, first is pouring cup. So pouring cup is a place where you pour the molten metal into the mold, and then the mold gonna flow into. So this part is the casting metal cavity. So this is a place where you form the shape of the part you want to make. Another thing is a core. So core is helping to shape the geometry of the part. Because with this shape you can see the metal actually gonna mostly flow into these places, right? So this is what it's supposed to be, what the shape's supposed to be. This is what the core is used to for. And also, by looking at the molds, actually it includes two parts, the upper part and the lower part. The upper part is called a cope, and the lower part is called a drag. So we first make the parts separately, and then I'm gonna put them together to form a whole mold, entire mold. After it's made, we're gonna separate them and then get the part out. Another thing I want to talk about is the riser. Okay, so this is a riser. So the riser's function is for compensating the shrinkage, and compensating the materials, for the shrinkage of the part. Because when this part is shrinking, so there's a less material formed in this shape. What happens is the riser, by storing some of the liquid molten metal, it actually gonna flow into the shape, or into the cavity, and then to compensate that kind of loss of material. So this is a loss of shape. So this is the function of the riser. So pay attention to this. When you are designing a riser, you have to think about that the riser needs to cool down later than the part here, because if the material in the riser cools down earlier than the cavity of the part, what happens is molten metal won't be able to flow into the cavity. Right, so that's why when you're designing a riser, you have to make sure that there's still molten metal in it, and it cools down later than the cavity. So this is about the riser. Later, we're going to talk about how do we make sure the risers can cool down later than the cavity. All right, so this is talking about the gating system and all the riser. I already explained this. So basically, riser must be designed to freeze after the main casting in order to satisfy the function. And so for the casting process, basically mostly we are casting the metals, and the heating furnaces are used to heat the metal to molten temperature sufficient for casting. And then what we do is we're gonna pour the molten metal. But there are some of the factors that determines the quality of the casting part. So these factors include the pouring temperature, pouring rate, and also turbulence. Pouring temperature. So when the pouring temperature is low or is not as high as it can easily let the molten metal flow, it means that some of the materials has already started to solidify, and there might be some of the air traps in there as well. So it might create some quality issues in the part getting to the cavity, the mold cavity. Also, the pouring rate. So pouring rate, if you pouring them at a different rate, some say the speed, right? What happens is that some of the material that you pour, at the very beginning that is really fast, it might solidify, and then later you pour it at a slower speed, and what happens is that they will, the part in there already solidify, and then you pour the molten metal in it, and it might also create some of the parts that is not evenly distributed the materials, right? Materials not evenly distributed in the cavity, and they might create some cracks or air traps as well. And same with the turbulence. Turbulence might create some of the forces between the liquid, and then it also gonna cause some imbalanced distribution of the material in the cavity. So when you are pouring the molten metal, you have to be careful and make sure you have a constant speed, constant flow, and also have a good pouring temperature. So the solidification of the metal means we let the metal to cool it down and solidify into a solid state. And solidification can be a pure element, pure metal, or it can be alloy. So, but the structure or the time. So the process actually are different. Now let's look at how different they are. First, for the pure metal, so what happens is the solidification will start from the wall, right? Because the wall is an interface that exchanges heat, right? Exchanges temperature and heat with the mold. So that's why when the molten metal start to interact with the surface, first we're going to create the wall that solidified already, that solidifies immediately. Then this kind of skin, thickness increases to form a shell. So from a shell, you can see the structure here. This is a surface structure. It's a little bit different with the internal structure, which is the center. Lastly, it's the center will start to solidify and create another structure. So this is why you can see three different structures in the solidification of the part in casting. And this is a pure metal. Now let's look at alloys. Alloys, because there are different metals in it, so we know that their melting temperature and also solidification temperature are different. Different metals have different solidification temperature. So that's why in this casting process, some of the metal will solidify first, while some other metal will solidify later. So that's why it will create different structures inside the part. For example, you also have a wall, have a surface, and then in the middle you can see there are two different structures formed. So this is how it's different in alloy casting. And so the speed of quenching or the speed of solidification, if it solidifies fast, what happens is it will create a very fine pearl-like structure. So it will be more like this. If it solidifies slower, it will create a more coarse structure, more like this. we know that if it has a more dense structure, the tensile strength tends to be a little bit higher. If it's a cooler structure, the tensile strength tends to be a little bit lower. And you can use this to have a comparison of the two. So this is why in a lot of the metal treatment or heat treatment, we can use this special character to increase the tensile strength, or to release the stress and increase the toughness. Now I probably want to talk a little bit about toughness and versus tensile strength again. Strength versus toughness. Remember, we already talked about it, I think, in 2 or 3 lectures before. So strength means how easily the material can be deformed, right? So it is measured how easily the material can be deformed. What toughness means how easily it can be fractured. Right, think about a rubber versus say maybe aluminum part. Okay, well, aluminum of course have a higher strength because it's hard to bend it and let it deform. Well, but with the force increases, what happens is the aluminum will either you can easily break, right? So that's called a fracture, and what happens is that it will fail. But for rubber, say aluminum. But for rubber, what happens is that the rubber, when there are some external force start to apply, the rubber will deform. So when it's deforming, there is a release of stress of the material. If there's no deformation, what happens? There's no release of stress, and stress will be concentrated at a certain place, and that's why it will cause fracture, easily cause fracture. But with a deformation, when it deforms, it will release the stress, and that's why it will make it more tough before fracture. To make sure you understand the difference between the strength and the toughness, and in most of the cases, strength and toughness are exclusive. Okay? All right. So for the solidification time, so there's an equation or some factors really determine how fast it solidifies, or the time for solidification. Actually, we can easily understand it because we have already seen it in our lives. So, for example, if we have pour some of the molten metal on the ground, what happens is that it can solidify very fast. Why? Because it has a really large surface, surface area, right? And so if it is we are pouring a lot of molten metal into a very small container, maybe the solidification time will be a little bit longer. That's because the surface area is small. So that's why the surface area is a factor that gonna affect solidification time. Same with the volume of the casting. Of course, if there's only a little bit of volume amount of the molten metal, then it can easily solidify. If it's a lot, then it takes time. So that's why another factor is the volume of the casting, compared to this surface area of the casting, and also it depends on the metal as well. So some of the metals might, because of the thermal, melting temperature, points are different. So some metal might solidify faster, some may be a little bit slower. So the metal itself will be a factor as well. And so for the mold, So mode is also a factor. So the mode, for some, if the mode transfers the heat easily, it means it can the solidification will become faster. If it is not, then it might be a little bit slower, right? So there are these are the main factors that determines solidification time. When we have this equation, okay, when we have the equation, we can use this equation to design the mode. Remember, when we're talking about the mode, actually, there's a riser, right? There's a riser. So the riser, we want to make sure the solidification time for the riser is longer than the cavity itself. Right, so we can actually use this equation to determine it, right? Because we have the same mode, right? Then we can use this V divided by A, right? V divided by A to make sure the riser's surface to area ratio should be bigger than the cavities or core, the mode's volume to area ratio. Then in this case, the solidification process will be longer. And this rule is called Cherevrov-Nov's rule. Now let's look at the shrinkage during solidification and cooling. The shrinkage process really starts, at the very beginning. After you pour it, it will start, from the surface starting level, and then what happens? It will start to have this kind of initial solidification at the molten wall areas, and also there's a reduction of the height. You can see there's a reduction of the height here. And then what happens? It will start to form a shrinkage cavity inside the part, right? So those cavities can be big, can be small, and eventually you will see there's solid thermal contraction, right? Contraction here, which creates a little bit of gap between the wall and the part. Solidified part. And this shrinkage actually it happens during both the solidification and the cooling. So occurs in nearly all metals because the solid phase has a higher density than the liquid phase. So when it solidifies, it will cause a materials volume reduction, and in order to compensate the loss of material, when we are designing a mode, we can design it with the shrinkage allowance, right? So which means the pattern we make for the mode actually we should correct for solidification shrinkage, right? And also thermal contraction by making the mold cavity a little bit oversized. So the amount of the oversize is actually called a pattern shrinkage allowance, okay? So directional solidification means it is to minimize the effects of shrinkage. It is desired that it starts to first let solidification start with a region that's really far away from the pouring region, right? And then later to have the regions that closer to the pouring place that is solidifies later. So that's why it will make it more smooth of the part, and also let the molten metal flow into the cavity. So this is the directional solidification. Now let's look at two different categories of casting processes, or two major categories of casting process. One is expandable mode process, and the other one is permanent mode. So expandable mode means we create the mode, and then after it's casted, the mode is gone, right, and or removed, or we are not using the mode anymore, or it is just destroyed. While the permanent mode means usually it's made of the metal or some other really hard materials, and we can reuse them. So next part we're going to use the same thing. Next part we're also going to reuse them. So that's two major differences. While for the expandable mode processes, we can create very complex shapes. As long as we can make them. For example, we can make some maybe use 3D printing to make the mold with very complex geometries, and then we just use that in the casting, and then after it's we made the casting with the shape, we're not the mold material is gone, right, or evaporated. Well, for the permanent mode, well, in this case, it's a little bit harder because the making of the mold actually is very expensive, and also there are limited geometries we can make with the current manufacturing processes. And one common casting process we see is a sand casting. So for the sand casting has been widely used in casting process. It's probably the most common casting process we see in our life or in industry. Nearly all alloys can be sand casted, including the metals with high melting temperature like the steel, nickel, and titanium. Also, we can cast very large size products to very small products as well. The quantity is the same. They can make a lot of a high quantity of parts with sand casting. So for the steps of sand casting, first we pour the melted metal into the sand mold, and then we allow time to let it solidify. After that, we're gonna break up the mold and remove the casting, and lastly, we're gonna clean up the casting and also to inspect the dimensions. So this is for the sand casting. We can see there's first making the pattern. So the pattern is a full-sized model of the part, right? It's slightly enlarged just to compensate the shrinkage and also the machining allowances in the casting. And the pattern can be the wood, can be metal, or can be plastic. All these patterns. The purpose of making the pattern is to just create that cavity, right, in the mold. So as long as we can make a really good dimension, as long as the geometry is right, the material is not a very very critical problem. So we are making the pattern. Also, we have designed the pattern for the riser, and also the cap pattern for the cope as well. Just because there's a gating system, we need to make sure that where the melted metal need to flow in, right? And another part of the mold is a core. So the core is to create a shape for the for the part. Because sometimes we need to make hollow parts at certain places. Then we have to insert the core in order to create that kind of geometry. Well, the core itself actually sometimes it cannot just stand by itself. We have to use some chaplet to give support in the make sure it's it will the core will be holding its position in the mold. The material of the chaplet is usually the same material as the one the molten metal, because eventually this will become part of the part as well. So that's the core and chaplet. For the mold, there are some desirable properties. First, the mold should have good strength, so it can maintain a shape and also resist the erosion, and also should the sand should have a really good permeability, because we can let the hot air and also gases to pass through the sand or the material, so it can release all those air traps or hot air, and also have a good thermal stability. Make sure it can resist cracking when contacting with the molten metal, and also it can be collapsed, right? So after the part is made, make sure it can be give away its shape, and so allow the casting to shrink without cracking the casting. And for the sand, usually it's we are using the foundry sand, and the main material is main element is the silica. We know silica has a really high melting temperature, so that's why you can use this to as the equipment or as mold for high melting metal castings. If the silica has a really good small grain size, means we can actually make really good surface finish of the part. Large grain size means the surface finish might not be good, but large grain size means there will be more gaps between the grains, and it can let the gases or the hot air to escape during the pouring. If we are using some irregular grain shapes, it can actually strengthen the molds, because those kind of shapes, grains can create some interlocking compared to some other grain sizes. But the problem is, if you create interlocking, means the less of the gaps will be created, and it will reduce the permeability of the mold. And sometimes we use binders, with the foundry sand. So sand is usually held together by a mixture of the water and the bonding clay. Typically, it's 90% of sand, 3% of the water, and 7% of the clay. Other agents can be, organic resins or organic binders, right? So these this kind of material, the agents will create either for increases the strength or enhance some other properties. So other than sand casting, there are also some other expandable mold processes. For example, the shell molding. So shell molding is a process that first we create a metal pattern. All right, so the metal pattern is heated and placed over a box containing the sand and mixed with thermosetting resin, and then we're gonna flip it, and the box is inverted so that the sand and resin will fall onto the shape, right? Fall onto the hot pattern. It will create a layer of mixture to partially cure on the surface to form a hard shell. So this is a shell. It creates at the surface of the metal pattern. And then next, the shell is heated in the oven, so we will create for complete curing. So we'll create this hard pattern shape with metal, and then also the shell mold will be stripped from the pattern as well. So this is how we make a mold, right? This is a part of the mold, and when we create the other part of the mold, male or female, and then it will create this kind of a shape shape of the mold. So this is where you can pour the metal in and create this kind of a product. So you can go back and watch this video about shell molding. I'm not gonna play it here, but you know when you are studying it, you should open up the slides and also go to the link and watch the video and see how what it looks like. For shell molding, there are different advantages and disadvantages as well. So the advantages is that it has a very smoother cavity surface, so it permits easier flow of the melted metal and also better surface finish. Or better surface finish means you have good dimensional accuracy, and also it minimizes the cracks in the mold as well. But the problem is that, or disadvantage is that it's very expensive to make the metal pattern, and also it's difficult to justify for small quantities. If you are making a lot of parts, maybe it's fine, but it's small quantity. It might have making just the pattern itself can be too much cost. Another expandable mold process is expanded polystyrene process. A more common name is called lost foam process. So lost foam process means we are using a foam to create the pattern or create the shape, and when we are pouring the melted metal, the melted metal actually evaporates the foam and then create that kind of a product shape. So that's why it's called lost foam process. So a benefit of this process is that we do not need to create two parts of the mold, and open it, close it. That it does not have to be that complex. It's complex. Only thing we need to do is just to create the shape itself, and then we bury them into the sand or into into the material, and then the mold material. And then what happens is just pour the metal. It will start to create the shape, and also the foam will evaporate. So this is what happens. Again, I encourage you to watch this video when you are looking at the slides to see how expanded polystyrene process or lost foam process works in real life. So the advantage of this lost foam process is that the pattern need not be removed from the mold, and also we can use very very cheap materials the foam, and also it's very easy to make the really complex geometries. The disadvantage is that a new pattern is needed for every casting. So every time you are making a new part, you have to make a new pattern as well. We have to think about how much cost you want to invest into the new pattern, and lost foam has been used a lot in making some of the engine blocks as well. And in this case, because the engine is very expensive, so that's why just using a foam to create that pattern actually is not much cost compared to the engine itself. So you have to give a little bit of economic justification of the process. So this is an example of aluminum engine head produced by the lost foam casting process. Well, another process is investment casting. So for investment casting, so basically the first we are creating a wax pattern. So the pattern is called wax because wax has really low melting temperature. Eventually, the wax will be removed. So after we create this wax pattern, then what's next is we're gonna put all these wax patterns onto or attach them onto a sprue, right, to form a pattern tree. Right, from a pattern tree. Then the pattern tree will be coated with a thin layer of refractory material. It's that refractory material that actually to form the mold, right? And next, what happens is the mold is held in an inverted position and also heated. So when we are giving a little bit of heat, the wax will be melted and then come out from the mold and then create all these cavities. So this is how we make this investment casting mold. And then after we flip it, it's we can pour the molten metal, and then this is how the parts are made. For investment casting, so every time we can actually make several parts all together. So in this case, we reduce the cost of making each of the part. And the part also can be really complex geometry. Yeah, and also we can have a really good dimension control and go surface finish, because we are forming a layer of the mold. Another advantage is that the wax can be recovered for reuse as well. But a disadvantage is that as you can see, there are many processing steps required, which means that you have to invest in equipment, in human labor, in energy, materials, into that's hard cost. So it's a very expensive process. That's why when we are using investment casting, actually we are making some of the very expensive parts. For example, the turbine blades, right? And also some of maybe the engine, some of the engine parts in airplanes as well. Well, another major category of the metal casting process is permanent mold casting process. In the for expandable mold castings, every time we are making a part, we the pattern will be destroyed. But in permanent molding casting, the mold can be reused many times. So it includes a basic permanent mold casting and also die casting. First, let's look at this permanent mold process. So basically, it uses a metal mold constructed of two sections, designed for easy, precise opening and close. So it will be similar as the mold or the die for, obviously, the mold, as in the injection molding. But the difference is that we are pouring the metal in it, right? In this case, the mold has to be have a higher temperature than the metal parts. Otherwise, it will gonna cause problems. So this is a permanent mold process. As you can see, this the left part is it's hydraulic cylinder to open and close the mold, and also in here, this is a part where it creates the cavity, and then the mold has two parts. When the cylinder pushes, you can see it creates a cavity. So and then you can pour the metal in it. Molten metal in it, and then will create the shape after it solidifies. After that, the mold is open, and you can get the part back. Of course, make sure when you are making this cavity, you also need to add a core if you are creating some kind of shapes. So the advantage of using permanent mold casting is that we can control the dimension and also surface finish. Because we can make it really accurate about the about the mode itself. It's very consistent because we're using always you are using the same mode, and also it can have really rapid solidification because it caused by the metal mode resulting in a finer grain structure, so the casting can be stronger. Also, there are some limitations. Because when we are making the mold, we are using the material of metals, so we can only produce the materials or metals with lower melting points. Also, it's a little bit so the geometries can be a little bit limited because we have to design something with an open and a closed shape. The cost for the mold is also a little bit high, and so when we are in the applications in production, usually because we do not need to change the mode, and also there's it can be automatic, so we can make really high volume production, can be automated. And typical parts for making using this kind of permanent mold process include some pistons, pump bodies, some small parts, right? And also some of the castings for aircraft or missiles as well. If you want to make the mold really big. Another process is for the permanent mold casting is a die casting. So the die casting, this is a little bit similar to injection molding, right? We use a certain pressure to push the molten metal into the die, and then to start to form the shape, and then solidify, then open it, and then we can get the part. And die casting machines mainly have two types. One is hot chamber machine, the other one is the cold chamber machine. Now let's look at the two different machines in die casting. So for the hot chamber die casting means, so the metal is melted in the container, and the piston injects the liquid metal under high temperature into the die. Now let's look at it. So you can see the three pictures, and in picture one, you can see there's a chamber, and what happens is that the chamber includes all the melted metal, and every time there's a plunger going to push the melted metal into the cavity at the left, right, on the left, and then the molten metal will start to form the shape, and then when the die opens up, it will create the shape. You get the part. And so this is why it's a hot chamber die casting, because we have a chamber is always holding this molten metal. Well, another process is a cold chamber die casting. Now let's look at cold chamber die casting. Here, instead of having a chamber that is full of molten metal, in this process we have an empty chamber that then we're going to use a ladle to pour the molten metal into the chamber, and use a ram to push the material molten metal into the cavity. So this is the cold chamber die casting. And usually, the chamber is made of a tool steel or mold steel that has a really high melting temperature. For example, tungsten or molybdenum materials. When we are for the mold, if we are making steel castings or cast iron castings. So the advantage for die casting includes that it's very economical for large production quantities because automation, and also we have really good accuracy and a surface finish, same as I think most of the permanent mold casting process have really good accuracy and a surface finish. And a disadvantage may include that it generally limits to the metals with low metal points as well. Just because of the mold is also need to be made of metal materials. Of course, if you want to make some of the high strength, high melting temperature, for example, ceramics, that's much higher. That's not another story. It's much higher cost. It might not be economic in some of the processes. Let's look at the casting quality. And same as injection molding for casting, there are also a lot of defects can happen in the process. Then we need to identify why it happened and what kind of process, what kind of these defects and why they happen and how to solve those. So generally, defects can be classified as two types of the defects. One is general defects common to all casting process. Another one is specific to sand casting. So one is called misrun. So misrun means it's a casting that has solidified before complete filling the mold cavity. You can see this misrun, right? When I'm pouring the metal, actually before the melted metal get into the end of the pattern, it actually already started to solidify, and it creates a place or a space that is without any kind of molten metal at all. So this is called a misrun. So what happens? Why it causes those? It can be when we are making this kind of molten metal, maybe it is not fluidity is not very good. When before it reaches the end, it actually already started to solidify and didn't really move that smooth, right? Or the pouring temperature is getting a little bit low. So pouring temperature a little bit low means it will start to solidify and also create maybe something that stops the molten metal to run into the end. Or your pour is too slow, right? Or the cross section of the old cavity is too thin. If it's too thin, it will start to form a block of the materials get into the pattern. Another type of defect is a cold shut. So the cold shut means when we are pouring the melted metal in it, the melted metal will flow into two directions, and then when it meets, it will start to form this kind of line there. And same when the reason it happens is because the solidification, right? And either the flow, either it's because of the flow of the material is not very well, and how do you increase the flow of the material? Either you can increase the pouring temperature, right? Or you can pour it at a more smooth rate, instead of if you pour it too slow, or all the rate is not consistent, it might cause this kind of issue. Another type is defect is a cold shot. We probably see this a lot. So which means that the cold shot means that's the metal spatters during the pouring, and also solid globules form and becomes entrapped in the casting. So this is a cold shot. More often we see shrinkage cavity, and so what it looks like is a depression in the surface, an internal void, it caused by solidification shrinkage. And when it shrinks, they actually start to create this kind of a depression. And so what you can do is if it shrinks, we just need to make sure we concentrate more materials in it. Where the material can come from, it's usually from the riser, right? So that's why you have to design a proper riser to have sufficient molten metal to flow into the cavity, so we can compensate the loss of the space of the shape. Well, when it's specific to sand casting, there are also some defects. One is called sand blow. So sand blow means that is balloon-shaped gas cavities, the gas trapped in there, caused by the release of mold gases during pouring. So when you're pouring it will have the gas. And so some of the reason the causes can be the low permeability. So the gas didn't really come out from the mold, poor venting, right, and or high moisture content of the sand mold as well. So in this case, you might want to increase the permeability of the mold. Also, sometimes we can see some of the pinholes. So pinholes are more like very small on the gas cavities, below the surface of the casting. Forming of those, usually that's because of the sand mold itself. You want to make sure it's the shape is consistent. And also the surface finish of the sand mold should be good as well. Another type is penetration. So penetration, the causing of the penetration is because of big gaps of the sand. So the molten metal actually start to get into the sand mold and start to create those kind of penetrations. So in this case, you probably want to control, the speed of the pouring. So because if the flow rate is high, it might cause this kind of issue because it just flows into the sand materials. And the solution will be hard packing of the sand, to make sure it's not sand surface is not loose. And last one is mode shift. So mode shift, we can easily see basically that's the cope and drag are not well aligned. It may create this kind of problem, and the part the part you made eventually was totally displaced, and usually it causes much more serious problem when you have this kind of mode shift. All right, so that's about all the major processes related to metal casting. Here are some of the quiz questions to make sure you can describe all these processes, and if you get familiar with those, you should go back and watch all the videos in the in the slides. This is to see how this process are actually used in industrial applications. All right, so that's all for today.